This is a talk entitled The Mathematics of Manifestation. It's a representation of a talk given at the Science and Nonduality Conference on October 25th, 2015 in San Jose, California. The essential thesis is that any enduring integration of non-duality with science must integrate non-duality with mathematics, which is at the heart of science. And the key to this is seeing how math is based on distinction and ultimately how distinction or duality is reconciled with non-duality. So the real challenge is integrating duality and non-duality. Science is based on mathematics, logic, and duality. On the other hand, non-duality teaches that duality is not real. So if distinctions are not real, how can logic and mathematics be true, and how do we account for an apparently objective universe? In other words, why does science work? Well, non-duality, first of all, teaches that distinctions are not real, and many fundamental distinctions are taken for granted by both science and common sense. Non-duality challenges the reality of these distinctions, states that they are not ultimately real. The philosophy of non-duality traces its origins in the Indian tradition with the philosopher sage Shankara, who stated that there is neither seer, nor seeing, nor seen. There is but one reality, changeless, formless, and absolute. How can it be divided? Now this may seem like an abstract philosophical position, but in fact you can examine this in our ordinary experience. So for example, consider this band of color here. On the left it's obviously blue, on the right it's obviously green, but where is the distinction between blue and green? It's not objectively given at any single place along that spectrum from left to right. We can, by convention, choose to draw the line at one place or another, but that is our choice and it's not dictated to us by nature. Another example would be the distinction between day and night. We think of these as obviously distinct and separate from each other, but upon close examination we see that there is no sudden switch from day to night. It's not dictated by nature at any instant. There is in fact a gradual transition, which we call twilight, which is similar to the transition between blue and green. So there's not one single instant where there is an objective distinction to be found there between day and night. Similarly, can we find a real distinction between land and sea? The waves are constantly moving in and out with no fixed boundary between water and sand. And even if we were to freeze it at any instant of time, the boundary between water and sand is not itself clear-cut. Some of the sand granules will be washed up and circulating in the water. Some of the water is permeating the sand, and there's no fixed distinction on that level. And even at the atomic level, you get down, and even the notion of position itself is indefinite. So this observation of the world, that no distinction can really be found, that these opposites really flow and transform into each other, was one of the teachings of the Greek philosopher Heraclitus. He said that everything flows and transforms into its opposite. There's no substance or thing that is graspable. So if this is the case, how is anything comprehensible at all? What is the nature of the apparently persistent objects in the cosmos? Well, in contrast with Heraclitus, Pythagoras taught that the cosmos is mathematically ordered. The way he put it was, everything is number. In order for the cosmos to be comprehensible, we need to have some sort of order in it. And for him, this was expressed in terms of numbers and their ratios. The example he liked to give was the musical notes. If you pluck a string, the different harmonies and octaves are all mathematical ratios of the fundamental. And so this harmony in the world is intimately linked with mathematics. And this is a reproducible result that you can find with any string. So this is a kind of order that's inherent within the cosmos, and it's essentially mathematical in nature. And this basic insight is alive and well today in modern quantum theory. The transitions of an electron in an atom between the different energy levels is expressed in terms of two integers. This wavelength coming off is determined by these different integers, just as the frequencies of the musical harmonies from a plucked guitar string are related to integers. And so this vision of the cosmos as a mathematical order is essential to modern physics today. And our fundamental elements of the physical world are described in terms of mathematical symmetries of elementary particles. It's different in nature from the Platonic vision of the elements in terms of these Platonic solids, but in both cases we have the fundamental elements being really described in terms of mathematical symmetries. The fundamental nature of the cosmos is not material in nature, but really mathematical. Werner Heisenberg, one of the founders of quantum theory, put it this way. He said, "But what was there in the beginning? A physical law, mathematics, symmetry? In the beginning was symmetry." This sounded like Plato's Timaeus. And this was also a vision that was an inspiration at the birth of modern science as well. Galileo said that the universe cannot be understood unless one first learns to comprehend the language in which it is written. It is written in the language of mathematics. So, although experiment was a key feature of the rise of modern empirical science, also this Platonic vision of nature being fundamentally mathematical was also essential. So, if we look at science, we see that it can be understood as the interplay between experiment and theory. We have, on the one hand, these mathematical models of nature. On the other hand, in modern empirical science, we test these experimentally. It's another key feature. So we have these two aspects of modern science that have an interplay between each other, the theory and experiment. The theory makes predictions, which we can verify in our experiments. And these verifications confirm the theory or may falsify it. In the case of the theory, it is described mathematically in terms of equations. And in terms of the experiment, on the other hand, we have quantitative measurements. And the interplay between theory and experiment is really mathematical. The experiments are quantitative measurements, mathematical numbers. The theories are expressed in terms of mathematical equations. And the way they interact with each other is that the mathematical equations of the theory are solved to give quantitative results, to make predictions, and they are either match the quantitative measurements or not. And so the real essence of how science works is on this level of mathematics. It really isn't so much to do with the philosophy. You can have multiple different interpretations of the same theory philosophically, but those aren't really the essential nature of science itself. We see this in quantum theory, for example. There are multiple different interpretations. There's the Copenhagen interpretation, the many worlds interpretation. These are, as it were, philosophical overlays, interpretations of the theory, and are not part of the scientific content itself. They don't correspond to different predictions. The predictions derive from the mathematics itself. And it's the mathematics that we confirm or falsify. It's not the interpretations. So you might say that even that the interpretations of the theory are not, strictly speaking, part of the scientific content of the theory at all. So let's take a look at some examples of how math is essential to these different parts of science. We have on the theoretical level, here's the Schrödinger equation of quantum theory. It's a mathematical equation that we can solve for different systems. In experiments, we make measurements. Here's the charge of the electron, and the key feature of these experimental measurements is that these are quantitative mathematical numbers and they are reproducible. Also, I should mention that logic is fundamental to science. We make logical deductions, both mathematically and otherwise, connecting our theories and reasoning about science and so forth. And logic also is essentially mathematical in nature. So let's look at this in terms of some examples to get a real good feel for it. In classical physics, Newton famously developed a mathematical formalism that applied to both terrestrial motions, these parabolic paths of if you threw an apple in the air it would follow a parabola, as well as celestial systems, the planets orbiting the sun or the moon orbiting the earth. And he used these same equations to describe both. The same equations could make predictions, quantitative predictions that would match our measurements, both our measurements of the positions of planets in the sky and our measurements of positions of objects falling through the air. So let's take a concrete example of this just to see exactly how it works. If we imagine dropping a ball from different heights of a building, first we set up a ruler, we mark it off, and we get a clock to time how long it takes the object to fall. In both cases, we are superimposing these distinctions upon a reality that does not objectively have distinctions built into it. But in order to make quantitative measurements, we choose a standard way of measuring distances and times. So we proceed to take a ball to the top of this building. Let's say it's 9 units high up there. And we drop it, and we find it takes 3 seconds to fall. So from a height of 9, it takes 3 seconds. And then let's say we drop it from 4, and we find it takes 2 seconds to fall from there. And then let's say we drop it from a height of 1, and find it takes 1 second. And of course, if we don't drop it at all, a height of 0 takes 0 seconds. So we then have this experimental data, and what we notice is that there's a pattern here. If we square the time, we get the height. So 3 squared is 9, 2 squared is 4, 1 squared is 1, 0 squared is 0. So this is our hypothesis, our generalization from this data. So we make a hypothesis. We say that, well, maybe this is true in general. And this allows us to make a prediction. If we take this general law, so we match this curve to the points we measured, and we can basically interpolate between them to make a prediction of a measurement we have not yet made. So we could say, let's predict that if we drop it from a height of 3, we will measure it to be 1.73 seconds it takes to fall. So that's a prediction. It may or may not be true. So then we go out and we actually test it. We take our ball to a height of 3, we drop it and time it, and lo and behold, it does take 1.73 seconds to fall. So we have, in this case, confirmed our theory. So that's a concrete example of how this works. So what we've shown here is that the real way that science works, this interplay between theory and experiment, is really an interplay between mathematical equations of the theory and mathematical quantities that are measured. So mathematics is really the essential foundation of empirical science, both in theory and in experiment. And that's the real foundation of science. Now, mathematics is a language that can be expressed in terms of sets. The measurements or numbers can be expressed in terms of simple kinds of sets, and the equations can be expressed in terms of more complex sets or relationships between sets. So, for example, the number 0 can be identified with the empty set. The number 1 is the set of 0, the number 2 is the set of 0 and 1, and so on. You'll notice that all of these numbers are basically defined in terms of just these sets, and there's nothing else involved here, just the operation of making a set. So sets are really just making distinctions. A set is really a distinction between what is contained within the set and what is not. So for example, the set of all fruit is the set of all x such that x is a fruit. You can imagine that as drawing a boundary, drawing a distinction between what is inside the set, what are members of the set, and what are not members of the set. So we have now distilled the essence of science down to mathematics and more essentially to the very notion of distinction. Here is where we see the real tension with science and non-duality, because distinction is really duality. It is presupposing that there are distinctions between true and false, between different numbers, between and so on. Without these distinctions, we couldn't do mathematics, we couldn't make measurements, we couldn't have equations. All of this is based on distinction. So in order to reconcile science and non-duality, we really have to address this core tension between the two. Non-duality teaches distinction is not ultimately real. So how then can science work? How can we understand science from this perspective? So this is the problem of science and non-duality. Science relies essentially on mathematics, which is based on distinction, while non-duality teaches that all distinctions are ultimately not real. So any enduring reconciliation between science and non-duality requires we address this fundamental tension between the two. It's not satisfying merely to appeal to some parallels between certain interpretations of quantum physics and certain non-dual teachings. We have to get down to the root of this difference between the two and resolve this before we can really say that we have a true integration of science and non-duality. So how do we approach this problem? Well, a clue can be found in Russell's paradox. It's a mathematical paradox that arose in early set theory, and it begins by forming what appears to be a perfectly reasonable distinction, a set. It's defined as the set of all sets that are not members of themselves. So the question then arises, is this set itself a member of itself or not? And this leads to a contradiction. If it is a member of itself, then it isn't, and if it isn't, then it is. You can work through the logic of that yourself, but it is a paradox, a contradiction in naive set theory. This paradox is showing that the naive notion of making a distinction is not necessarily always going to be what we expect it to be. We can have these apparent distinctions which, when you look at them more closely, actually break down. So one solution to this is to only allow certain kinds of sets to be created in the first place, to constrain the construction of sets to guarantee that they're consistent. And this is what's called the cumulative hierarchy of well-founded sets. And this avoids Russell's paradox, but it's based on the empty set. And the empty set is the set that contains no set. And what's notable about this definition is that it makes reference to the notion of set. And so we're starting our idea of sets by making a set, and we say, well, this set, how do we define it? It's the set that contains no sets. But we are appealing to the notion of set here when we're making this set. And so even though there's no set within it, it's implicitly making reference to the notion of a set. So we're kind of in a self-referential paradox here at the very foundation of even these sets. And similarly, the definition of distinction itself assumes the notion of distinction. In order to define what it means to make a distinction, we have to say, well, a distinction is doing something. It's drawing a line or a boundary such that what is on one side is not on the other side. And this is a definition, and it relies upon making distinctions. And so we are relying upon distinctions to define what it means to make a distinction. And so this is a circular definition. If you examine distinctions, even in mathematics, just as we saw with the apparent distinctions between night and day and blue and green and day and night, superficially they seem to be obviously distinct, but upon close examination we see that we can't actually grasp onto a distinction there. We can't actually find it. And the point here is that the same is true in mathematics. When we really get down to examining these distinctions, we can't actually find them to be objectively existing. And in this case, the definition of distinction is circular. So it arises only by assuming that, that we already have one. So the solution really is to acknowledge this, that this is the nature of distinction. Distinctions are not objectively real. They're only apparent. And then, acknowledging this fundamental nature of distinction, to then, from this new basis and understanding of distinction, then derive mathematics from distinction and see science as unflowing from that. And this really transforms our whole vision of the nature of mathematics and science, to understand this fundamental nature of distinction. So symbolically, we could say that a distinction is an arising of an apparent boundary between, say, inside and outside. It isn't, this circle isn't quite closed. In fact, if you look closely, it doesn't make a distinction, but superficially it sort of appears to. And so that's the beauty of this, is that it appears to be making a distinction, but in reality it doesn't. That's the key insight here. But if we ignore this, this lack of reality of the distinction, it appears to be a complete, consistent distinction. And then if we take that as an assumed basis, that there really is a distinction, then these distinctions can start to, we can have more than one distinction, we can start to relate them to each other, and mathematics can unfold from this apparent reality of distinction. So we might say that the absolute reality is that which transcends identity and difference. It's beyond change and changelessness, things and nothings, duality and non-duality. Because distinction is not real, making a distinction doesn't change what is real. So reality, we could say, is invariant to making a distinction. And this, you could say, is the definition of non-duality. So this omega here is the symbol for reality, and the brackets around it is the symbol for making a distinction. And so reality is equal to reality with a distinction made. So the distinction does not change reality. Shankara would put it this way, that despite the appearance of distinction, reality is non-dual. So he would say, no matter what a deluded man may think he is perceiving, he's really seen Brahman and nothing else but Brahman. This universe, which is superimposed upon Brahman, is nothing but a name. Distinction could be understood as a kind of symmetry. Symmetry is a mathematical way to express invariance to change. So the nature of distinction is symmetry, a difference within identity, a variance within invariance. Reality is this invariance to making a distinction. So if we consider this triangle, for example, if we change it by, say, rotating it, it doesn't change. It comes back to exactly how it appeared before. If you had closed your eyes for that moment while it was rotated and opened them again, you wouldn't be able to say whether it actually rotated it or not. So mathematically, we could say that the the rotation operator r applied to the triangle leaves the triangle unchanged. So the triangle is equal to the rotation of the triangle. This is a kind of symmetry operation, or a fixed point. And similarly, the reality, the omega, is equal to the reality with the distinction applied. We operate upon reality and we don't change it. And so this is a symmetry. This invariance to change with respect to distinction is a symmetry. Now, if we break this symmetry, and symmetry breaking is a fundamental idea in physics and how the physical world manifests. The essential idea of breaking a symmetry is to say, okay, well, let's say that the recognition of this underlying unity or invariance is ignored or not recognized. The difference then appears to be real. So we make a distinction, and it appears to be a real distinction now. This breaks the symmetry. And now we have duality. We have what's inside apparently distinct from what's outside. And from this starting point, we can start to develop mathematics. We have distinct things, and we can start to relate them to each other. We can say that A can be arrived at by making a distinction of B. A is the opposite of B, you might say. Also, if you take the opposite of A, which is B, and the opposite of that, you get A again. So A is the opposite of A. And if you put A and B back together again, you have A and its opposite, which gives you back the original reality again. Out of this naturally unfolds certain mathematical relationships and equations, and a kind of mathematics naturally unfolds from the symmetry breaking. And in fact, you can take the notion of distinction and out of this develop these kinds of laws and transformations of distinctions, and you can get what is essentially Boolean algebra and the laws of logic. Conventionally, Boolean algebra and logic are notationally expressed in terms of and or and parentheses and not and these different logical operators. In terms of distinctions, however, it's incredibly simple. There's only one operator. It's the making of a distinction. There's nothing else. This serves to completely represent all of the logical operations just by making a distinction. Another key feature of this is that distinctions are both the things that are operated upon as well as the operators that do the transformations between them. And so we have a unity of operator and operand. And from this kind of symmetry breaking, mathematics unfolds here. We have logic. If we take this process further, we can get a kind of arithmetic, basic arithmetic of integers. Laws unfold, and you have different kinds of distinctions, and these interplay with each other and transform, and you can get addition and subtraction, and you take it further, and you can even get multiplication, division, exponentiation, logarithms, square roots, and basically all the arithmetic you would need to represent numbers that we measure in experiments, as well as their relationships with each other. You could actually take the t squared equals h equation and represent that in terms of distinctions. Our complete picture now here has our theory and our experiment. Essential to that are the mathematical equations, which we can represent as distinctions on the left, and then our mathematical measurements, which we can also represent as distinctions on the right. And so all of science can be seen as this play of distinctions that arises out of symmetry breaking from non-duality. The apparent distinctions, which are not real in the ground of non-duality, if that symmetry is broken, that fundamental symmetry of the first distinction is broken, then distinctions apparently arise and mathematics unfolds from that, and we can see mathematics and science as fundamentally growing out of distinction. And this is what I call the mathematics of manifestation. Out of non-duality, from the symmetry breaking process, manifests this mathematics, which is really what is the essential nature of science, both in theory and experiment. We can generalize this even further. I'm just going to mention this as an aside here, that our religions and mystical teachings rely upon distinctions in language as well, at least the spoken and written teachings. And these symbols are based upon distinctions, and they have their root in non-duality in just the same way. And at this very fundamental level where the first distinctions in both cases in mathematics and the symbolic language of mystical teachings are starting to arise, we can actually start to make correspondences between the two at this fundamental level, and we could express certain mystical teachings in terms of mathematics. So here are a few examples to whet your appetite or tease you a little bit. Neti neti could be expressed in terms of distinctions this way: not this and not that, not this one thing and not this other thing. The pointy brackets are the not, and the this and the other thing are the curly brackets and absence of them. So it's neither this nor that. Nagarjuna said form is emptiness and emptiness is form, or samsara is nirvana. And this is really the fundamental symmetry of reality, to either making a distinction, making form, or not, emptiness. So the invariance to making a distinction is the identity of form and emptiness, nirvana and samsara. So this is the equation expressing that teaching. And Lao Tzu said that the Tao that can be told is not the eternal Tao. So in that case, he's making a distinction between what can be said, what is form and what is emptiness. What we're saying about the Tao is not the eternal Tao. So in that teaching, there's a distinction between the two. So this work is part of the mission of the Center for Sacred Sciences to help foster the creation of a new worldview in which science and the teachings of non-duality can be viewed as different ways of describing the same underlying reality. If you're interested in learning more about this vision, please visit our website. It's at centerforsacredsciences.org. Thank you.